Testing, testing. All right, so we're good. And another test going on, linear test or something?
Yeah.
Ouch. Well, did you have a linear test? You took it already. How'd you do?
I got B.
Yeah.
It was a rough class, so.
Yeah.
But I think a lot of people, probably only a few, maybe 3 people who got A's in it. So.
Mm-hmm. Yeah. So they're probably going to be coming in about a half an hour, I guess.
Probably, yeah.
Philly lets them go late, which is.
Yeah. Well, I'll raise him myself. He's not in this semester. He's with me.
Okay, he's got something else going on though. I think he has to drive his mom somewhere. Yeah. Well, I mean, you're here, and the lectures will be available for people to look at online.
Yeah.
No point in doing problem solving because you didn't get it. So you got some friction in physics 3A, right? And this is the basis of friction. So pretty important topic for mechanical engineers. If you're a civil engineer, probably not so much. You're mechanical?
Yeah, probably.
Okay. Well, so we're going to be looking at certain types of applications of friction, of boxes that tip or slip, and wedges, belts, bearings, kind of stuff. Well, we're not going to do bearings, but we'll look at belts, wedges, kind of basic machine type stuff for mechanical engineers. The notion of friction comes around from the observation that sometimes when you pull on something, you actually are applying a force to it, but it's still not moving. And the reason it's not moving is that there are these interactions between the atoms of the two different surfaces, where they actually, I guess they sort of weld to each other through a kind of a weak bonding mechanism. I'm not really too familiar with how that actually works, but that bonding mechanism resists the motion, and it provides an internal force at that boundary that keeps the thing from moving. There's some diagrams here that kind of show you these. I don't know how to interpret that. This is, I don't know if are these the atoms or in between, but anyway, what it sort of amounts to is that you get these, it's almost like a distributed load as you're pulling this thing. You get this, well, there's a normal force. The normal force we talked about is sort of the force pushing back, keep the thing, the weight from pushing it down into the gravity, into the Earth center. And then friction force are at each one of these atoms or whatever, micro things, they're actually providing resistance to that motion, which keeps the thing stationary to a point. what we do is, since we're comfortable with the idea of simplifying a distributed load, we can simplify both the normal force and those little friction forces into a simpler diagram where the normal force is acting at some point O, and the friction force is also acting at that point along the surface, and it's opposing the direction of motion, or the direction of the force that's applied to it in this case. And typically we don't really worry about this model, we just kind of focus on the normal force and the friction force. Just use that as our basis for analysis. Interesting things happen when you start to pull on something, and there is this point where the this force F, which is depicted here, and this force P, which is depicted here, can be plotted on an XY curve. And the idea being that as you start, pulling up on, increasing the force to the right, the P load, the friction force matches that perfectly to remain, to keep the box in equilibrium, right? So the friction force follows that. It's a 45-degree angle, F equals P in this region, and it just sort of tracks it all the way up. So, if you're applying, like, say, 10 pounds of force on this box and it's not moving, well, that means the friction force is also doing 10 pounds opposing that motion. You go to 20 pounds, and, the friction force, oh, I forgot to get Windows Office 2013. It's on my to-do list. And then, but there comes a time when the friction can't keep up anymore. The bonds actually start to break, and you reach a limit. This is the limit of static friction. And there is a special notation for this. Fs is the limit of static friction, and that is μs, the friction coefficient, times the normal force. And the coefficient of static friction. So this is the coefficient of static friction. Which is the limit beyond which the friction force cannot hold anymore. So the point P at which that happens is called the P force for impending motion. And then once it starts moving, the friction force will actually decrease. So once you cross that force, you are getting less of a friction force. This is the what's called kinetic friction. This is the limit of static friction. Now, in our class, we're only going to be looking at the static part, but if you take a dynamics class, you'd start to look at the kinetic friction part and do some analysis of when the thing's actually moving. That's a different limit, and in this case, I should erase this because there's no room here. This kind of comes over here to this thing called FR, which is mu k times n. The kinetic friction coefficient is what FR becomes. So, and I guess, I don't know how that actually works, but it seems like, once things are moving, the kinetic friction coefficient is constant. So, but we're not really concerned about motion. We're just concerned about things in their stationary form. And we're looking at the limits of when things are going to start to move. The kind of problems that we solve in statics are, what force do you need to get this thing to start moving, or to keep it from sliding, and that kind of thing. You can experimentally determine the coefficient of static friction in the lab if you put it on a ramp. but in this case it's sort of flat. But if you start pulling on this thing, the angle of friction is the angle between the resultant force. If you add these two forces vectorially together, F and N, this is not a good picture of that. This would sort of look like that. The resultant force, R sub S. And that's the combination of these two forces together, which is sort of the net force acting at that point O. And that force has an angle phi sub S to the vertical normal force. And the tangent then of that angle phi sub S is going to be the ratio of Fs over N. But Fs is mu S times N. And so that means that's just mu S. So the tangent of that angle is mu S. That means the angle itself is the arctangent of mu S. This is significant because you can actually experimentally determine the static friction coefficient by putting like a box or whatever material you want on a ramp and just keep increasing the angle until it starts to slide. Once you find that angle that it slides at, then mu S is the tangent of that angle. That's the friction coefficient. So that's pretty cool. So the kinds of analysis we're going to do, first we might have to know, well, is this body going to be in equilibrium under these circumstances? True or false? If it is going to move, is it going to slip first? Is it going to tip first? If you push a refrigerator from the top, is it going to tip over? Is it going to slide? You know, some of those questions. Or what is the force of impending motion if this thing's going to move at a single point, or if there's multiple points where the thing can move? You know, which is the force that's going to make the whole thing start to move? It's at one of those points, or at some of those points, or at all of those points. So here's a typical problem. This is on the handout, I think. So the question is, will the 200-pound crate slide down the 30-degree incline if the coefficient of static friction is 0.35? So the standard way to analyze this is to draw the free body diagram, draw all the forces acting on it, and write the equations of equilibrium. You may need to tip the axes so that it kind of works okay, I guess. You survive the linear test? Is that just the second test? So you just have two tests and then a final? Ah, okay. You had the first test was last week? We have 2 days in Monday and Wednesday. Wow. You had 3 tests in linear? My test, yeah. Which I also was not feeling too good. So linear we had 3, 1, That's a lot of testing. At least you have Friday off, right? Yeah, no class Friday. So yeah, as far as things go, I'm doing the lecture on friction today and I think tomorrow. So I guess the friction assignment will be due the following Sunday. And so if you still have homework 11, you can turn that in on Monday. If you haven't done that yet. If you turn it in or you want to rework it, just feel free. But so grab a handout. Grab one for Jose. He's coming in right now. And I just did the intro to friction, which you can catch on the video, but we're just doing the first problem, so this is a good time. Trying to let go of the stress of the linear test, and like there's no friction at all. It just slides right off you. What's going to stick? What's going to stick is this, because this is a lecture on friction. So we're doing the first example problem. The question is, you got a 200-pound crate, you got a 30-degree incline. The coefficient of static friction is 0.35. Is it going to slide or not? And this is where we can now place bets. You want to bet whether it's going to slide or not. Who thinks it's going to slide? 30-degree coefficient of static friction is 0.35. All right?
I don't know.
Don't know. Yeah, well, we could take bets and then decide, and then do the analysis, and then see who has the right. No, it's not going to go. You think it's going to stay? Okay, good. All right, we got a diverse selection of choices. There is a quick way. We were just talking about the, well, just to kind of catch you up real fast. Sorry, Matthew, but the idea of friction is these little atomic forces that keep a body from moving when you apply a force to it. The forces are actually acting at the boundary between two surfaces, and they actually act like little wells. And so the little atoms are actually kind of sticking to each other, and until you actually break those bonds, the body's going to stay stuck there. And so you have a force P that you're pulling on the box with. The friction force can be reduced to a solid F, a single F. The distributed normal load can be turned into a single normal force. Operating at some point O, and that slides in order to keep the moments from making the box tip. And the curve is such that, you know, the friction force tracks the force that you're pulling to keep the body at rest up until the point where the friction force gives up. You start breaking those bonds, and the body starts to slide. And that point is the limit of static friction is when P equals mu s times n, which is called Fs. That's the most friction force you can get based on your you know, the materials involved. And mu s is the coefficient of static friction. You learned this in physics. I know they covered this in 3A. Yeah, there's a max friction force, at which point if you pull a little bit further than the max force, the body's going to start moving. And that force is the force that we're interested in a lot of problems that we're going to do. What is that force of maximum force, you know, the limit of static friction? Once the body starts to slide, we're not really concerned with this area because this is dynamics, but once the body starts to move, the friction force drops a little bit, so it kind of keeps moving. Once you kind of cross that threshold, it wants to go easier. You know, you get that refrigerator started moving, it's a lot easier to keep it going, right? But if it stops, you got to push a lot harder to get it moving again. The way you can determine this experimentally is you come up with this angle, which is the angle between the resultant of the force, friction force, and the normal force applied at point O relative to the vertical line there. It turns out this angle is the arctangent of the friction force limit of the friction force over n, the normal force. And that's what we call, because friction force is, this limit of the friction force is, the limit of static friction is mu Sn. Mu s is the coefficient of static friction, important number. You divide the ends out, and basically the tangent of this angle is mu s, so that the angle is the arctangent of mu s. And what that means is if you actually just took a box and put it on a ramp and angled the ramp up, the point at which the box starts to slide, you take the tangent of that angle, and that is, or the arctangent of that, you take the tangent of that angle, that is the coefficient of static friction. So you stick a box on a ramp, and you find the angle at which it starts to slide, sliding just from the force of gravity alone, and the tangent of that angle is the coefficient of static friction, which is the limit at which the maximum friction force that you can actually apply, and the thing will remain stationary. Once you exceed that force, it will start to slide. And n is the normal force. How heavy is that thing, right? So the heavier the body, the more friction, the more force it's going to take to get it to move, right? Heavier refrigerator is harder to get to move, right?
Oh, and
that one? That one? Yeah.
Oh, I see. So you have the NR that included So you just figure out the angle.
You can do it experimentally. It's really easy to do. They should do a physics lab on this. They probably don't, but it would be an easy one to do. It'd be a good statics lab. And again, we're trying to find whether things slip, if they tip, what force required to make this thing start moving. Those are the kind of questions we look at. Here we are, the first problem. We've got a crate, 200 pounds, 30-degree angle. Is it going to slip or what? Is it going to stay stationary? So when you're given a problem like this, you start with the free body diagram as always. The weight of this thing is 300 pounds. That means you've got, or 200 pounds, you've got a 200-pound force of gravity pushing down on it at the, say, assuming it's the middle of the body, right? And the normal force is going to be acting somewhere to the left of that. So it's going to be something like that. I apologize for this mess that my pen keeps doing. I just haven't gotten Office 2013 installed yet. Hopefully that will fix it. The normal force, maybe I'll just go do it the way I did it before. And the friction force, F, opposing the motion, right? There. Okay, and the analysis can be helped by tilting your axes so that you have an x-axis that goes up the plane, a y-axis that goes normal to the plane, or the ramp, the incline. And you can see that it's possible to express the weight in these x and y coordinates. So you have a wy, that's in the direction of your tilted y-axis, right? And you have a wx, which is in the direction of your tilted x-axis. You're just decomposing that 200-pound force into a wx and a wy. Okay? And yeah, and this angle here is going to be 30 degrees because this is a 30-degree angle of theta right here, right? Okay, we're just setting up the free body diagram so we can write these equations, so it's actually really straightforward. This is, again, the same angle. You know, this angle here, 30 degrees, is the same angle as this angle here. That's theta there. It's the, you know, this is the geometry thing, being able to read those angles properly. It's also this angle right here. Oops, theta, not phi. So the sum of the Fy's equals 0, and that's going to be, in this case, n, right? And minus w sub y, the y component of that weight. What about the 200? Well, wy is the amount of the 200 that's acting in this tilted y direction. Yeah, so that's going to include that. It's going to be in there, right? That wy is, what is wy? If we have this angle 30 degrees, right, wy equals what? 200 times the cosine of 30, right? Right, so therefore n is just equal to wy, which is 200 times the cosine of 30 degrees. And that equals 173 pounds. Okay, the sum of the fx's is going to be, what do we have in the x direction?
WX.
Yeah, got wx in the minus x direction, right? So we're going to have minus wx. What else we got? And the friction force, right? F minus wx. And Wx is just 300 times or 200 times the sine of 30 degrees, right? So F is going to be 200 sine of 30, which is 100 pounds. The question is, can the friction force get that big, right? I mean, that's the, if we're in equilibrium, right, that's what the friction force is going to have to be to keep the thing from slipping. Isaac?
So essentially, the first part, we find that WY is like visually how does that work?
Well, if you tilt your head 30 degrees to the left. Yes. Then the normal force is tilting. Now the normal force looks like it's going vertically up, right? And the WY force is going straight down, right? Yeah, they are opposite. So that's why it's N minus WY. That's all we're doing. We're just tilting the X and Y axes. Is it?
To recap those forces in your direction is the force that
the normal force is keeping the box from going into the incline, right? And the friction force is keeping the box from sliding down the incline. The normal force is keeping WY from pushing the box this way, right? If the normal force wasn't there, the box would go like that. If F wasn't there, the box would go like that. So all we've done is we've just figured out these. This is if the box is not moving, this is what the forces have to be, right? But we know there's a limit to how big the friction force can actually get, right? What's the largest friction force you can have? Nope. Stop. What's the limit? What's the largest friction force you can ever get? The limit of static friction on this diagram, right? In other words, that says friction. Limit of static friction. It's the coefficient of static friction times the normal force, right? Meaning the heavier the object, the higher the friction force it can actually give you, right? Okay. At that point, it starts to move, right? The friction force is tracking the pulling force all the way up until it hits that limit, right? So if we're less than the limit of static friction, is the box going to move or not? Yeah, if we're less than the limit of static friction, the box stays stationary. If we're over the limit of static friction, the box starts moving. So the question is, so we basically saying this is assuming that it's not slipping, right? We made an assumption here that it's not slipping, and this allows us to solve for F and N. Okay. However, we've got to check our assumptions. We assume that it's not slipping, but is that correct? So the assumption is that's going to be true if F is less than or equal to mu S times N. Right. In other words, is 100, which is what the friction force has to be for that thing not to slide, is that less than or equal to, what's mu S? 0.35. This is like hell for teachers. 0.35. Yeah, like my worst nightmare. Every time I write something on the board, it gets garbled. I'm in this class. It goes on forever. I'm doing a lecture, and every time it screws up. Okay. Well, what is the prognosis? No, 100 is not less than 0.35 times 1. It's bigger, right? No. So it is not at equilibrium. Our assumption is not correct. This is the assumption that we made. We assumed that it was at equilibrium, and then we checked our assumptions. We tested the limit. And the limit is that the maximum friction force is mu Sn. If we exceed that limit, then it's not at equilibrium. So the answer to the question is, will the crate slide down the 30-degree incline? The answer is yes. Yes, with a garbled up Y. Right. So that inequality is incorrect, right? So in other words, we can only be at, because F, right? So as we go back to the slide, the friction force is going to match whatever force it needs, you know, whatever force is added to it, applied to that box to make it slip, it's going to match that until it reaches that limit. So the friction force is not always mu Sn, it's going to be whatever it needs to keep the body from moving. But then at a certain point, it can't do that anymore, so the body starts to slip. No, it does not have to be equal. So in other words, if the friction force that we analyzed was, say, if it turned out that, you know, this F was, say, 20 pounds. If we found it was 20, then what would be the prognosis? It's static because it's less than 173 times 0.35. See, yeah. If you have a bigger static friction limit, is that what you're saying?
Yeah,
if the coefficient of friction is bigger, then it's going to keep it from, if the coefficient of static friction is bigger, that's one way to keep it from slipping as well, right? Yeah. Mm-hmm. Yeah, all righty. So that's the kind of problem that takes place with friction. And another way we could have done this, because we talked about that angle, right? The angle of that, you know, tilted box. So F has to be less than mu S times N, meaning that F over N has to be less than or equal to mu S. And the tangent of that angle actually is, has to be less than or equal to the tangent of phi. And that means theta has to be less than or equal to this phi S, you know, for equilibrium. That's the one we actually did in this other thing. That's called the angle of repose, for the whole thing to be stationary. This phi is the angle of this angle between the resultant and the maximum friction force and that normal force, and that is the arctangent of the coefficient of static friction. Anyway, the point is we could have figured that out just by taking the arctangent of mu S would give us the angle at which it would still be stationary, right? And we have a calculator. What's the arctangent of 0.35? 19 degrees. So in other words, once the angle got above 19 degrees, it was going to slip. Right, so phi S, so theta has to be less than or equal to the arctangent of mu S, which in this case is 19.3 degrees, for it to be stationary. So that would have been a quicker way, like if you just, you know, if you had to do this in a hurry, you just took the arctangent of the coefficient of static friction and said, well, that's the point where it's going to start to slide. So 19.3 degrees is where it was going to slide. So you're over that, 30 degrees is bigger than 19.3 degrees, so it was going to slide anyway. And you don't have to do all this analysis. But you have to have more experience before you get comfortable with that. All right. These are really fun problems that often have this question of what's going to happen in this situation. Later on, there's a boy dangling from the side of a cliff, and a woman, presumably his mother, trying to hold him up with a rope. And the coefficient of static friction on her shoes is like 0.35. Is she going to be able to keep him from falling? Can she pull him up? These are the questions that we get to answer in this week's assignment, chapter 8. So here you have the big crate that you're working for a moving company, and it's a 400-pound crate, and for some reason, maybe you have a forklift, it's pushing it 8 feet off the ground. So now the question is the crate going to slip or be stable if you're applying a 125-pound force at 8 feet above the base of that crate? It has a base width of 4 feet, and it weighs 400 pounds. Again, you have too many unknowns in friction problems, so you have to assume certain things and then sort of check to see if your assumption was correct. If it wasn't correct, then the other thing happened, right? Question? So we say, all right, let's assume that it's in equilibrium. And again, we're going to label these guys. Here we have a weight, W, on it. And this point O kind of shifts. We'll talk about why it's shifting in a moment. And the friction force F is like that. And the normal force N is up like that. And it has shifted from the center line a distance of X. We'll come back to that X value. It's doing that because if it doesn't, the body's going to tip because you're going to get a moment, right? That P applied 8 feet off the ground, and the F opposing it is causing a moment. And if the normal force doesn't shift, the thing's going to tip over, right? Does that make sense? Right? Since P and F are, until the thing slides, P and F are the same force, that gives you a couple. A couple is a tendency to tip. The reason it doesn't actually tip is because the normal force location starts sliding to the right to present a counter couple. Isaac? Yeah, we just picked O arbitrarily. We just said O as some distance X. Do you understand why it has shifted to the right? Bless you. As I was just talking about, you get a couple because P and F are providing a clockwise couple, so N has to slide over to provide a counterclockwise couple between N and W to keep the body from in equilibrium, right? Again, if it's in equilibrium, all these things are going to be true, so the thing doesn't actually tip. So if it's in equilibrium, though, we know that the sum of the Fx's has to equal 0. So therefore, F is going to equal P, or 125 pounds. The sum of the Y forces equals 0, means that the normal force is going to equal the weight, which is going to be 400 pounds. Okay, so everything good? Question is, we found F, we found N. What's our check? Is F less than or equal to mu S times N? Is 125 less than or equal to 0.35 times 400?
Wouldn't it be clockwise?
We're not doing couples just yet. These are some of Fx's and some of Fy's.
I don't think you said
Yes, the moment between W and N is counterclockwise. The moment between P and F is clockwise.
Oh, okay.
Mm-hmm. So 125 is less than or equal to 0.35 times 400, right? So what's the prognosis? Yeah, 0.35 times 400 is like probably 140 or something. What does that mean? Sorry? It hasn't slipped yet, right? So this means it does not slip. Okay, with me so far? But the question is, what if it tipped? Could it have tipped? Well, we didn't check the moments yet, right? This is something now, it's a tall box, you're flying high up, you got a big couple moment, right? P times 8 feet is the couple moment clockwise, is a normal force. Going to be able to slide far enough to the right to be able to provide a counter couple. And what happens if it can't? It tips over, right? So, see, right? So P and F form a couple. It's P times 8 feet, right? And it's going clockwise. And W and N form a couple. And it's basically W times X, and it's going counterclockwise. Okay, so that's an interesting thing, right? If it's still in equilibrium, again, we're going to assume it doesn't tip. And this is sort of assuming equilibrium for forces, and this is assuming an equilibrium for moments. So we can take the sum of the moment about O, and that's that point where the normal force has slid, and we say, all right, that's W times X. Right, W times X, that's counterclockwise, and minus P times 8, that's clockwise. That has to equal 0. And that will equal 0 if X equals, right, we can now solve for X, 125 times 8, that's P times 8 over W, which is 400. And that equals 2.5 feet. That's how far the normal force has to slide to the right from the center of that box in order to provide a couple that would counter the couple of P times 8 feet. Is that possible? Yeah, it's the X value between the center line and the normal force. Is that possible? It's not possible, right? Because you only have 2 feet to get to the edge, right? So that means your assumption is not valid. The max X is how big? Is 2 feet. At that point, when X gets to be bigger than 2 feet, it's tipping. So just to plug that in, if you are at the max X, then you're not in equilibrium, right? The sum of the moments about O are going to equal 400 times 2 minus 125 times 8, and that's going to equal minus 200 pound-feet. And that is a net moment going in the clockwise direction. That means the crate tips. Okay, so these are the other kind of problems, you know, tipping crates. You have to kind of make these assumptions. You're adding these extra variables like x because that normal force is sliding to the right. As the p force gets bigger, it has to provide that counter couple. Okay, questions? That kind of wraps it up for today. We'll pick up from here tomorrow. So yeah, based on all these tests we're having, if you haven't done homework 11 yet, you can turn it in on Monday. And this is for homework 12. We'll have this due the following week. Yeah, we're going to slide, so a little extra breathing room. It's the least I can do. How'd you guys feel on the test? I haven't looked at them yet.
Yesterday?
Yeah.
Oh, yesterday. Oh, yesterday.
Oh, yesterday. That one. What? The only one that matters to me. Well, they are somewhat extra credit. They're 50-50. So if you got half of them right, then balances out. I designed it so that if you did half of them right, that's all you needed. All you needed to get was half of them right, and then you would. Yeah, if you did them all right, you get a little bit. Right. Okay. Right.
If you did them all wrong,
5 points out of 100. If you just blew them off, you lost 5 points. If you did them all and got them all right, you could get +5. You could get +5. And there were some pretty easy multiple choice questions. All right, I've got to run.